I can flip it eventually.
Okay, so you have a disk with the mass m and a little m in here. The disk has a radius a. So to find what is the magnetic, gravitational force of disk on this little m, you make it small, chop the disk off into small rings. Okay, rings that have a radius little r. So when you have this little ring here, this little ring is going to create a force, act by a force on a little m with a dF force, right? dF ring. So now the question is, if you want to find the force by the disk, you can add all the F rings from 0 to A, from here to here. All these rings will add the little F, will contribute to the total F. Does it make sense?
Yes.
Now let's go back and find what is the force of the ring on the particle. So we'll come back to that. Now we have an only ring with the radius r and the mass m. And let's say this ring has a mass big M, okay? So in this case, I'm gonna chop this off into small elements that I'm gonna call a dm. So I already know this little element and this little element, how to find the little force that is acting on this m. So this is gonna be a d little f, right? So symmetric element on this other side will give me a force that is on this direction, still df, right? There's always the symmetric pairs everywhere. So when you resolve this into components, these two, this will have x components, this will have x components, they will cancel out. But the y components are actually going to add up together. Is that making sense? So if I have this one is called x, and let's call this one theta, then the total f for the ring would be the sum of all little df elements, the times cosine theta. Okay, the vertical component of it. So now let's try to understand what's the cosine theta. If this is r, this is x, and those are constant, and this is the distance between two elements, let's call it s. Okay, so then my cosine theta, my cosine theta equals x over s. Now df, so you have two little particles, right? M1, M2, so the distance between them is s. F equals g m1 m2 over s squared. So I'm going to do the same thing in here. I have g times little dm as one particle, m as this other particle, divided the distance is s squared. Okay, so I'm going to plug these two in here. So this goes here, this goes here. That equals integral g, let me bring that m in front of the dm, m dm over s squared times x over s. So that equals, let's take all the constants out. I'll end up having g, m is constant.
I think it's running out.
I need another pencil. Thank you. Gm
Cut.
x over s cubed integral dm. Okay? Well, you can put an integral as a m ring, and then that would be m ring. Or you could just call this is dl and integrate through the surface. But this is an easy way. So you could do gmxm ring over s cubed. That's it. Now that we got for the F ring, we can go back to our disk. So let's take this one to the ring. In this case, now my little element has a mass of little dm. Okay? Not little, big dm. So that's the mass of the ring. I'm going to substitute mass of the ring with a dm here. So I'm going to write integral g m x m dm over now s cubed. Well, let's remember what was the s. S from here equals square root of x squared plus r squared, correct? So I'm gonna have it substituted here. So gmx is a constant, gmx, and then dm over, so square root of x squared plus r squared cubed. Okay, gmx integral dm over x squared plus r squared 3 over 2. Now my integration goes by r, so it has to be from 0 to a. But I can't do integral by dm, so I have to figure dm out, right? So let's just do our density, mass density thing. So this is an area, so I can say dm equals sigma times dA, okay? Sigma being a big M over the area of the disk, which is M over pi A squared. Now, the little dA, it's not a little dA, but the dA equals, okay, if I cut this ring, it's gonna be this long. So this little thickness of the ring is dr. Because, see, this is r, dr, and I'm integrating by r. So that's this thickness, dr. And this is the circumference of the ring, which is a 2 pi little r. So that equals 2 pi r times dr. 2 pi r dr. Okay? So I'm going to plug all that stuff into here. So sigma is a constant. I'm just going to keep it as a sigma, bring it out, and then put it back later. Gmx sigma integral, instead of dA, I'm going to put the 2 pi r dr over x squared plus r squared 3 over 2. So equals gmx sigma times 2 pi integral r dr over x squared plus r squared 3 over 2. I can solve this now. Let's go from 0 to a, 0 to a. U substitution r squared, right? Du would be r dr. Is it 2 r dr?
Yeah, it's 2 RDR.
2 r dr.
And then you get just
So then r dr equals du over 2. Well, you plug it in, you end up having, I think from this point on, you know, right, what to do. So I'm not gonna change the limits because I'm gonna come back to the r anyways. So that is du over u 3 over 2, 1/2, and this whole thing in front. Okay, sorry. And then I'm gonna let you do the rest. Okay?